unmute. All right, yeah, we're getting started. My name's Victor Solo. I'm a professor at the University of New South Wales in Sydney, Australia. I'm an engineer. I'm also a statistician. I've been collaborating at the Martinos Centre for nearly 30 years, in fact. So I used to be a Harvard faculty a long time ago. And so I figured I earned the right to decide arbitrarily that I would give a talk. Okay, so enough of that. Let's yeah. Oh, yeah. Let's see if we can stick it down there. No, that's not going to do. Okay, how do I minimize? Oh, that's the trick. Great, thanks. Okay, so look, I thought a couple of things, talking to some colleagues after coming back after a long COVID break. So colleagues in general, new colleagues in Patrick's lab, Patrick Perdon. So I had collaborated with Patrick 20 years ago, and now we're starting up again. That I ought to spell out the story of network construction in a coherent modern way, because the state of that in the current neuroimaging literatures is piecemeal, to say the least. So, and I've tried to grind some of this down to, I don't want to say lowest common denominator, but something nearby. So let me say this, if you don't remember anything else out of this talk, or you don't get anything else out of it, there's two things I want you to get. The first one is this quote here. So this is from a paper in BMC Systems Biology 2007. It's a genomics paper, but you know, those guys have similar problems with network construction. And it says, the use of correlation networks is widespread in the analysis of gene expression. Well, you could say fMRI and MEG in place of that, and proteomics data, even though it's known that correlations not only confound direct and indirect associations, but also provide no means to distinguish cause and effect. I'll be talking about cause and effect later. It's the direct and indirect associations getting confounded, which is a huge problem. Which conditional independence graphs overcome? This is a picture of a little conditional independence graph, which I'm going to go through in great detail in a moment. So that's the first point, the confounding. If you think you're going to build scientific theory off correlation networks, then I think you're going to have problems. Okay, so we got stuck again. Is that it? Oh, thanks. You're going to tap that first. Okay, so look, here's an outline. What I'm going to do is take you through the first few pages of Whitaker's book on conditional independence graphs. And by the way, when I say graph, you can also think network. So the theory I'm going to outline began to be developed in the stat literature in the 70s. There's been an enormous development since then, and this was the first book, 1990. I still regard it as the best book. It's incredibly clearly written. And, you know, usual story, something new comes along, a lot of work gets done, things mature a bit, people start writing books. So this was the first one. Okay, and he's got this brilliant little example at the beginning, and that's what I want to show you. Then I'll start talking about, because the example is on a tiny network, scaling things up. Then I'll start talking about what I call vector networks. I'll describe these things later, and I'll start talking about conditional mutual information and give you an fMRI example. Then I'm going to go to the frequency domain. This is relevant from a couple of different points of view that I'll get to. I'll mention Granger causality, and I'll give some examples. And then I'm going to outline, let's call them open problems in network construction, and a summary. A bit of an issue with terminology. There's either univariate and multivariate, or scalar and vector, and I'll end up mixing the two together, and so do the different literatures. Conditional correlation or partial correlation, same thing. Graph or network, same thing. And I could go on. nodes and links versus edges and vertices. So there's at least one mathematician in the audience, but I don't like those terms, vertices and edges. I find the link and the node easier to conceptualize. Okay. So here's the very first page in Whittaker's book. I've left all the words in. We're not going to read these words. I'm just going to show you some numbers and a few pictures. But I wanted to emphasize the fact that this really is the first few pages in his book. And so some of you not quantitatively comfortable might find later parts of his book difficult to swallow, but you won't have any trouble in chapter 1. Okay, so he's illustrating what this methodology can do with some maths grades from high school kids. I'll show you the data in a moment, but he's got a couple of histograms here, and you can see a distribution of these things, and the algebra and stat marks have got different centers or means in their histograms. So here's the marks, and the subjects are mechanics, vectors, algebra, analysis, and stat. And here's a couple of scatter plots. It's vectors versus algebra and stat versus algebra. And as you'd expect, there's clearly some kind of relation here, approximately linear, in fact. Okay, he then goes on to calculate the correlation matrix, which appears over here. Now, if you look at this correlation matrix, you can see some decent sized numbers. And by the way, because there's 88 subjects, the standard error is roughly plus or minus 0.2. So they're all statistically significant. And, you know, they're not too bad, of the order of 0.4 to about 0.7. So that's great. Everything's correlated with everything else. But that's basically the end of the story in terms of correlation. There's really not much else you can say. You can't get any structure out of there. You can't get any insight into the nature of these correlations. And the reason is because everything's mixed up. It may be, for example, that analysis and mechanics are correlated, not because there's some underlying cognitive relation between them, but because they're correlated with something else that's driving them in some way. So you need to get rid of the effect of these possibly confounding variables. So the way to do that, you regress mechanics on the other three variables you're worried about, vectors, algebra, and stat, get some residuals. You regress analysis on those other three, get some residuals. Those two sets of residuals now represent those variables with the effect of the others adjusted for. You now correlate those two things. That gives you a partial correlation, a measure of the direct association between those two variables, having adjusted for the effect of the others. So that gives you partial correlations. And of course, there's apparently a stack of regressions to be done. There's actually some neat math, some linear algebra, which shows you that you don't need to do all the regressions. You can actually get all this by just inverting the correlation matrix and then rescaling it to make it a pseudo correlation matrix, and you can read them out. And so this is what he's done. So have a look over here, the rescaled inverse covariance matrix. Now, by the way, first thing to notice, the minus signs. It turns out that partial correlations are minus the entries in this inverse correlation matrix. So that explains the minuses. But the really interesting thing is you have a look in the left corner, and you can see 4 of these partial correlations are very close to 0. So what Whittaker then does is draws an abstract version of that down here. So an asterisk is something that's non-zero, and the zeros are then shown. So that's kind of interesting. And from this, he constructs a graph or a network. Here it is. So the rule for constructing this graph or network is that 2 nodes will be joined if there is a non-zero partial correlation connecting the 2 variables. And if the partial correlation between 2 variables is 0, there's no link. So for example, mechanics and analysis have no link because that partial correlation was 0. Okay. Now just notice Whittaker hasn't shown the link strengths. The link strengths will be useful is just trying to show the general idea here, but you do want to have the link strengths later, so you can actually measure the strength of the partial association. So he's now got some explanation, interpretation, and this is extremely important, and I'm going to read these things in a moment. I just got a side comment. Many of you will have heard of structural occasion modeling and path analysis, which is a special case of that, although it's the original version of that from the 1930s. There is a connection, although incredibly, there's basically no literature discussing the relation. There's one paper I know of, incredibly, in the neuroimaging literature, Marolek, from about 2009, I think. Although, let me just say, I don't entirely agree with some of the things he says, but we'll leave it at that. The conditional independence graph I've got so far is unexceptional. That's not the quite right word. Structural equation modeling path analysis remain controversial because you're attempting to get a causal inference out of observational data typically, and that, that's a problem. We've got more sophisticated ways of doing that. There's a whole story there. Some of them developed by colleagues in the School of Public Health at Harvard, like James Robbins. But you can get to those things from here by adding additional assumptions, but I'm not going to go into that. So let's have a look at Whittaker's interpretation. First point, this construction reduces the complex 5-dimensional object into two simpler 3-dimensional ones. We've got two 3-node subnetworks. That's what he's talking about. Second thing is it groups the variables into two sets: mechanics, vectors, algebra, analysis, stat, algebra. So that's kind of interesting. It highlights algebra as the one crucial exam in analyzing the interrelation between different subjects in exam performance. If we imagine doing some kind of a cortical version of this, we might start trying to call algebra a mediator. We might be thinking of thalamus or something like this, okay? And then the last one, it asserts that algebra and analysis alone, so these two guys, would be sufficient to predict stat. You don't need to worry about the others. It won't make any difference. And similarly, algebra and mechanics alone, for example, would be sufficient to predict vector score. But if you wanted to predict the algebra score, you need to use all the other 4 variables because this guy is linked to all the others. So the conclusion is that this graph or network constructed based on direct associations is actually enabling you to get some insight into hidden structure in that data, which you'll never get by looking at a correlation network, again, because you've mixed up the direct and the indirect associations, okay? So again, this has been understood for a long time, but it also seems to be taking a long time to make its way into some of the applied literature. So these are my 2 points, the initial criticism, and then this simple little example. If you don't remember anything else, this hopefully should, cause you to be a bit concerned about some of the things that are being done to your expensively collected data. Okay, so that's great, but that was... Yes. No, that's a good question. Absolutely, yes, for sure. And of course, from our context, they're not time series, but the concept is the same. Okay, so that's great. That was a 5-node network, but when we move to fMRI, MEG, EEG, or genomics, we're talking about much bigger networks. So even if we took a modest 90 size parcellation, say of fMRI data, you have got, well, I've got the 167, which is out of our paper that I'll be showing you. But by the way, the pictures I had on the second slide, that's out of our paper, which I'll be talking about later. So you've got 167 choose 2, which is about 14,000 partial correlations. there's no way you're going to look at those things and decide that, you know, some fraction of them are zero. So what to do instead? Well, the simple thing to do would be to go through the process I just described. So you calculate the 167 by 167 correlation matrix, you invert it. Now you from somewhere find a threshold level and you basically threshold them. If they're smaller than this, they'll be set to zero. If they're bigger, you keep them. There are data-dependent methods for choosing that threshold. I don't want to get into that kind of stuff. Things like AIC and BIC for those of you that know a bit more about these things. But here's the crude method, which is more or less what I just described. You just do that threshold. And in fact, that's what we've done in our paper, as I'll explain later. But it's not statistically efficient. And of course, the statistical efficiency begins to become a big deal because, for instance, with my colleagues, we're trying to apply some of this to clinical scan data, 6 minutes worth. We need every piece of statistical efficiency we can lay our hands on in order to make things work. Okay, but to get going, one might start with something cruder. So what are the kind of methods you could use to get statistical efficiency? Some of you will have heard of these sparsity penalized regression methods. The lasso is pretty well known now. I just want to make a side and excuse my typo here. I just want to make a side comment. I've got 1994, 96. So 1996 is the paper by Tibshirani, famous computational statistician at Stanford, published in a stat journal. And a lot of people refer to that as the beginnings of this sparsity revolution. It's not really true. When you look at the history of science and technology, there are always precursors. I'm not going to bore you with that history. But this is a very interesting situation where, and those precursors typically are not the general thing. And, you know, the person who often gets the credit is the one who kind of saw the big thing and wrote the paper putting it all together. This is an unusual example where the big thing was already put out 2 years before Tibshirani in a major journal, IEEE Transactions on Signal Processing. And the two guys that wrote it, Alany and Rosinsky, nobody's ever heard of them. It's a very sad story, and I've, for the last 20 years, been plugging them whenever I got the chance. So I've got a reference to their paper at the end, if anyone's interested. It's a beautiful piece of work, and it's got a stack of maths that Tibshirani doesn't have. Okay. Then the way this would work is that you would write down a likelihood function based on the covariance matrix, and you're going to penalize those off-diagonal partial correlations. So how is that done? So here is my attempt to explain it to you in a half of a slide. I'm just going to look at the simplest possible example because I just want to get you to understand the idea of these sparsity techniques and how they work. So I'm going to have a look at a least squares problem. I got one data value. I want to fit one parameter to it. So if I don't have this penalty, I'm going to use a least squared method. I'll just minimize y minus beta all squared. Well, the minimum obviously occurs when beta equals y. So no problem. But let's have a look what happens if I add a sparsity penalty, lambda times the absolute value of beta. So your initial thought would be, okay, I'll minimize this using calculus. Unfortunately, it doesn't work. Why? So have a look at this penalty term. If beta is positive, the derivative of that is just +1. If beta is negative, the derivative is -1. So the derivative has got a discontinuity at 0. It jumps from minus to +1. And for those of you that know the maths, then you know that that means that the calculus approach can't work. And you have to use a different approach in order to minimize this thing. And here's how you do it. So in the next line, I multiplied everything out, y squared minus 2 beta y over 2 plus beta squared over 2 plus lambda beta. And then I notice there's a beta here and a beta there, so I'd like to collect them together. Beta is equal to its sign, plus or minus 1, multiplied by its absolute value. And similarly, y is equal to its sign multiplied by its absolute value. And so that enables me to pull an absolute beta outside. And then in the square bracket, I got the lambda minus the product of the two signs times the absolute value of y. Okay, so now here's the interesting thing. Those signs, they're plus or minus 1. So when you multiply them together, you'll either get a -1 or a +1. But if lambda is greater than or equal to the absolute value of y, it doesn't matter what those signs are doing, the square bracket is positive, or maybe 0. That being the case, it's obvious looking at this expression that it can be minimized by setting beta to 0. Okay, so this is the really interesting thing, because what it tells you, if your absolute data value, absolute y, is less than lambda, then the minimum is at beta equals 0. So you exactly zero out the coefficient. Okay, so this is unusual. This is not a calculus that most of you would be used to. Now, what happens if lambda is less than absolute y? Now you can use calculus. You can do the optimization when beta is positive. You can do it separately when beta is negative. Not the only way to do it. Put them together. Here's the formula for the minimizing beta when lambda is less than absolute y. And notice that it actually snips a lambda off the absolute y. So the interesting thing is you get an automatic zeroing of the coefficient depending on this threshold. Okay, so that's the basic idea. And then, you know, we can do more maths and we can extend this and we'll have many betas, and this simple solution isn't going to work. You have to do everything iteratively. But this is the central idea of automating the thresholding. And because you've done it by modifying the criterion that you're optimizing, in our case with a covariance matrix, it will be a penalty on the likelihood function. This will enable you in principle to get closer to statistical efficiency. The L1 is not the only penalty. There's all kinds of other things. We don't need to get into that. Okay, so this is how you scale up. This is how you tackle zeroing out large numbers of partial correlations in a very big covariance matrix. So I'm going to give you some examples of how that works in a minute, but before that, I just want to keep going. So I now want to introduce what I call vector network, and I'm also going to introduce conditional mutual information. So again, think of the parcellation I was talking about before, 167 parcels. So that's typically going to have thousands of time series within each parcel. And that's what I call a vector network. So a vector network is one where each node, in this case parcel, has got more than one signal attached to it. In the fMRI case, it'll be time series, a similar thing in the MEG, EEG. A scalar network is where each node has only got one signal. And what everybody basically does, or almost everybody does, when they get to that parcellation, they'll typically do, in each parcel, they will do a principal component analysis, and they'll keep the top principal component, and that reduces the signal dimension in each parcel to 1. So you've now got a scalar network. You can calculate your correlation matrix. The problem is, in doing that, you've thrown out masses of information, because typically that top principal component might explain 10% of the variation, maybe somewhat more, but not 90%. So you've spent millions of dollars buying a scanner. You've spent months, if not years, getting an R01 grant. You've spent more months filling out forms and getting IRBs to go to collect the data, recruit the subjects. Finally got all the data, and the first thing you do is throw most of the information in it out the window. When I first began to realize this was going on about 15 years ago, I was stunned like a rabbit caught in the headlights. It took me a while to wake up. I thought I was missing something, but I wasn't. Okay, so massive data wastage. And it's not just neuroimaging, just about any other literature now. I mean, there are people analyzing streaming networks. The sociologists have been looking at networks, of course, for decades. But as large networks, the kind of data to support them became available, people just kind of went into some automatic mode of doing what I explained. throwing a lot of information out the window. So the question is, can we keep all that information? And if we could, presumably we could do things better. Well, the story I told you with the partial correlations, the same story applies, but now because I'm keeping those time series, now actually what we do is we do a principal component analysis, let's say of several thousand time series in each parcel, and we keep enough components to maintain about 95% of the variation. And that turns out to be on average roughly something like about 200 or 250. So we do get some dimension reduction, but doesn't take you down to 1. So you can repeat the partial correlation story, but you will now get partial correlation matrices, right? So if you've got 2 nodes, each of them got 250 time series, I regress all that against all the other nodes that have now got a couple of hundred time series. It's a bigger regression, but when I'm finished, I get vector residuals. And when I take the correlation between them, I'll get a partial correlation matrix. Now, what am I going to do with that? I can't tell the nice little story that Whittaker told because it's a matrix. How do you get a simple interpretation? The answer is you need to find a scalar measure of that multivariate quantity. And that's what conditional mutual information will do for you. So I've got the classic reference, Cover and Thomas. Cover is a famous professor of electrical engineering at Stanford. The book is just absolute classic, just crystal clear. I mean, it's just a cut above any other kind of work. It's amazing the guy could explain this stuff so clearly. Now, yes, of course, there's quantitative stuff in there, but still, it's just brilliant. It's been through a couple of editions. Now, before I go on and tell you a little bit about mutual information, I need to make an important point. So if you go and do a search on the web, you'll find a lot of people using mutual information to do various kinds of things. Communication engineers, of course, have built, all the cell phone networks and all that stuff, and they've been doing this with telephone exchanges while not using information theory since the 1900s. So Shannon was the guy who came up with information theory, another MIT professor in the late 40s. But application outside communications engineering maybe begins in the 60s, I would say. You can find a lot of stuff on the web. You can find people using mutual information in fMRI and MEG, but they are not doing anything related to what I'm doing. So the conditional word is crucial. None of them are using that. That's a huge deal. The second thing is there's some kind of automatic desire to only keep the top principal component when you're trying to dimension reduce all the time series in the parcel. There seems to be an ingrained rut where everybody who wants to apply mutual information to some image processing or signal processing problem tries to do it non-parametrically. And I'm not going to do it non-parametrically because the dimensions are much too big. So you won't find anybody doing things the way I do, and I'll show you what I'm doing more clearly on the next slide. Okay, with all those caveats, let's have a look at this thing. So multivariate mutual information, I'll start with. Scalar measure of multivariate association. That's a crucial thing. It's a scalar measure. It's symmetric in its arguments. So 2 random vectors, X and Y. The mutual information between X and Y is the same as the mutual information between Y and X. And what is it? It's the expected value of the log of the ratio of the joint density divided by the marginal densities of the 2 random vectors. And I've written out the integral here. But you can see a crucial thing. If X and Y are statistically independent, in fact, if and only if they're statistically independent, then the joint density will be the product of the 2 marginal densities. So that ratio will become 1. So the log of 1 is 0. So the mutual information vanishes if and only if the 2 random vectors are statistically independent. This is absolutely crucial, okay? And furthermore, I'm not going to prove this, but you can show that I've said it, this mutual information is always greater than or equals 0. Okay. So 0 if and only if x is perpendicular to y, where by perpendicular I mean independent. I've rewritten now, hopefully you'll have some memories of conditional densities. So for example, the joint density divided by the density of x gives you the conditional density of y given x. So you can also say that the mutual information is the expected value of the log likelihood ratio between the conditional density of y given x divided by the density of y. Again, you can see immediately if y is independent of x, the conditional density of y given x equals the density of y, you get a 1, you get the mutual information to be 0. But the other thing is that this gives a connection with statistical stuff, likelihood ratio methods for hypothesis testing. And one of the great puzzles of all this stuff is that statisticians, by and large, have never picked up on mutual information. It's really quite a puzzle. You'll find the odd statistician trying to use it to do something, but most of them, it's just not part of their vocabulary. And yet it's just the expected value of likelihood ratios that they use all the time. So kind of interesting. They do have some things that have mutual information interpretation. I'll mention something later. Now, I want to get to the multivariate conditional mutual information. It's a simple extension. So the conditional mutual information of two random vectors x, y, given another random vector z, symmetric in x and y, it's the expected value of the log of the ratio of the conditional density xy given z over the conditional density x given z multiplied by the conditional density y given z. And it vanishes if and only if x and y are conditionally independent given z. And you can immediately start thinking of that now multivariate network. I'm not going to have a link between the vectors x and y if they are conditionally independent given all the other vectors in the network. So basically what I'm doing is I'm going to use this scalar quantity, conditional mutual information, to zero out the links in my conditional independence graph, okay? So this is the thing that nobody else except Whittaker has realized that you can do. And Whittaker, unfortunately, didn't really know much about information theory. So he's got some stuff in his book, but it's kind of written in a strange way, and he doesn't really do much with it. So this is one of the things I claim I've picked up and started to use with a vengeance. Okay, so so that's gives you an idea of what this conditional mutual information is doing. Now, the next question is, how do you calculate it? Well, before I do that, I need to show you a couple of crucial properties of this thing. It's got some very nice properties. There's something called the chain rule. So you can decompose the mutual information between y and a vector set of random variables, x1 to xn, into a sum, where you basically have a sum of conditional mutual information. So you got all these variables x1 to xn, you order them in some way, and then you can do this decomposition. And if you have a different order, you'll get a different decomposition. So this is a bit like doing analysis of variance in a regression problem where the regressors are not orthogonal. If the regressors are orthogonal, then you have a unique decomposition of the total variance into a sum of contributions from each variable. But if they're not orthogonal, you have many different decompositions. You may be lucky to be able to choose one, maybe depending on some underlying theory you've got about what's going on. So this is really a generalization of that idea. And in fact, statisticians who use GLIM models, not to be confused with GLM in fMRI, which is inappropriately named. GLM in statistics really does refer to a class of general linear models, whereas unfortunately in fMRI, because of one person whose name I won't utter yet, this general term is being used for a specific case. But GLIM is something else, general linear iterative models, generalizing regression to distributions from the exponential family, where you get similar nice properties. And there's algorithms and stuff, and there's something called the deviance, which gets decomposed in a kind of analysis of variance. So this stuff has been around now for 4 or 5 decades. It's widely used, and I'm just drawing the analogy. maybe more understandable for most of you is this crucial property. If I multiply the vector X, the vector Y, the vector Z by 3 different matrices, so maybe I'm doing some pre-processing, then you would hope that the conditional mutual information doesn't change. And indeed, it doesn't. It's brilliant. So linear transformation will not change the conditional mutual information and the mutual informations. However, some of you may have heard of conditional distance correlation. It's been doing the rounds now for about a decade, and a lot of people in various applied disciplines are using it to try to do things. It does not have this property. So if I change the scale of X and Y and Z, the distance correlation will change. That's weird, but the mutual informations will not. So the conditional mutual information has got a stack of properties which are intuitively satisfying and furthermore practically useful, meaningful, and you know, the kinds of things we want to have. I've just got a little formula here. I've applied the chain rule. I'll leave it as a homework exercise for you to look at the chain rule and see if you can derive this thing down the bottom. My point was to show that one way to calculate the conditional things is that you can get them from just regular mutual informations if necessary. Okay, now how am I going to compute all this stuff on a big network? I'm basically going to use Gaussian formulae. And my argument is we kind of know, roughly speaking, fMRI data appears to be reasonably Gaussian. And similar thing maybe with EEG, MEG. The proof of the pudding is, and I'll show you some results from our paper in a minute, this works. From a mathematical point of view and a statistical point of view, it's a bit problematic because, of course, if the joint distributions of the data are not Gaussian, then I'm not calculating the correct conditional mutual informations. But of course, if they're close to Gaussian, I should do a fairly good job. And I think there's also a theorem for the odd mathematics type here, which would enable me to show that this is a functional on the data that's got some nice properties, but I haven't quite got there yet. Anyway, we don't need to worry about that. So if you do those integrations using Gaussian distributions, in the scalar case, you get simple formula that the mutual information between X and Y is -1/2 the log of 1 minus the square of the correlation. So if you had a correlation network, I can just use this formula and convert it into a mutual information network. They'll be the same thing, just with different units. Indeed, if X, Y, Z are jointly Gaussian, then the conditional mutual information, these 3 things being scalar, is -1/2 log 1 minus the square of the partial correlation between X and Y given Z. So I could go back to that little diagram of Whittaker and replace his partial correlations with conditional mutual informations. But they're essentially telling you the same thing in that case. Where it gets interesting is in the vector case. So the mutual information between 2 random vectors is given by this formula, -1/2 log determinant I minus R transpose R, where RXY is the correlation matrix. So here you see we've converted the matrix into a scalar quantity. And the scalar quantity vanishes if and only if the whole matrix RXY is 0. Okay, and that just follows from the definition. It's a determinant. So that's the important result and really enables everything I'm doing. And then again, if X, Y, Z are vectors jointly Gaussian, then you've got this formula for the conditional mutual information, -1/2 log determinant I minus R transpose R, where RXY given Z is now the partial covariance matrix between X and Y, having regressed out all those Zs. Okay, so again, we got the scalar measure. And again, this is going to enable us to build these conditional independence graphs. So that's basically the story. And then again, if we keep it this simple, we just need to find a threshold and then we'll zero them when they're under the threshold, remove the links. Where do you get the threshold from? This is actually a huge problem. And basically, one would like to develop a theory. I'm still working on that. Needs some really advanced math, random matrix theory. partly to do with cursive dimensionality. So instead, we're doing simulation. We simulate a network of the same dimension consisting solely of white noise. Everything is white noise. We pump that through these computations, and then we can get null distributions of the link strengths. And the interesting thing is this. So think of the example I'm talking about, 167 parcels. The data I'm going to show you is Human Connectome Project data, 1,200 time points. Even after the principal component reduction to about 200 time series in each of the 167 parcels, I've then got about 14,000 variables, but I've only got 1,200 time points. So I've got a singularity problem with my covariance matrix. So that's another story. I'm not going to focus on it too much. But my point is that in that scenario, it turns out these null distributions have got structure, surprising structure. And this was actually first realized in the fMRI context by Ed Bullmore's group. So, you know, Ed Bullmore has spent a lot of energy over the last couple of decades trying to apply graph analysis methods to fMRI networks. And at one stage, they decided to have a look and see what happened if they simulated a white noise brain and pumped it through their processing stream, and discovered to their great surprise that they found small world network in this white noise brain, which of course should scare the hell out of you, because you have hoped and expected there's no such structure. But it's because of the singularity issue. So there's massive amounts of noise still because you don't have enough time points, okay? So, and this random matrix theory is the mathematical theory that could handle that. The problem is this particular problem, it's not one that's been tackled yet. So I have done a bit of work on random matrix theory. It's really hard stuff. Okay, so now I think Bullmore's group at that stage, I don't really think they knew what to do. But what I'm saying is you do all that, you get the null distributions, and basically now you take the upper 95 percentile of the null distribution. That's going to be your threshold. You're above the white noise artifact. And so on average, or at least with high probability, everything you see after that is something real. So that's what we've done. And again, remember, that is not statistically efficient. So one of the things that we want to do is do this sparsity stuff. We're writing an R01 grant to see if we can get some funding to do that, amongst other things. So let me just show you these results quickly. I'm not going to dwell on this for too long because we're getting close to time and I've got a few other things to say. So this is joint work with a stack of our colleagues. I've got a colleague slide towards the end. So we use Human Connectome Project data, 10 subjects, 4 scans each, 1,200 time points, 167 parcels, a couple of thousand time series per parcel. I've said some of this before. We do the PCA to keep about 200 components, which gives you about 95% of the variation. You would now have to, there's a couple of problems. The covariance matrix, the correlation matrix is singular because of this problem of not having enough time points. So the inversion of a singular matrix is problematic. There's maths to help you try to do it, but the inverse is not unique. And then there's also the problem of inverting gigantic matrices reliably. To cut a long story short, we worked out a fast algorithm that enabled us to kind of finesse some of this stuff. And okay, here's the result. Now, I'm not going to, particularly not going to try and do any interpretation. That actually is a huge issue all by itself, which we hope to work on in the future. Okay, so what have we got here? This is the correlation. So the straight correlation where you did the principal component and kept the top component, except we converted it into a mutual information. And the redder the things are, the stronger the link is. And well, you can see, you know, there's a mass of stuff there and it's mixing up the direct and the indirect relations. And this is a bit of a problem. What we got next to it is partial correlation approach to the same thing using sparsity. So when you've got the scalar variables, there's already literature and algorithms in the stat and the machine learning community doing this, and we applied that. So this guy, it's not a fair comparison because this guy is using sparsity and none of the other things are. But nevertheless, you can see you've got something interesting there, cross hemisphere connections and all that kind of stuff. Down here is the multivariate conditional mutual information, where we did that pruning after we did the massive simulations to get the null distributions. You can see there's a lot more stuff than there is in the sparse one-dimensional thing. Here is DTI. Now, yeah, we know DTI's got its own problems, but we would expect structure and function are related to each other. I guess we're all trying to find out how. So therefore we might expect there should be some relation between the two. And at least just, eyeballing the thing, you can clearly see there's quite some similarity. Of course, that's not going to pass for real science. But let me put it this way. If the result did not bear any relation to DTI, end of story, no need to look any further, but it does. So there is a need to look further. So that gives you a rough idea of what this looks like when you go and do it, and indicates quite clearly that using all that extra information really is getting you something that looks, in principle, quite substantial. More comparisons. I'm not going to go through this stuff, but obviously we did other approaches to comparing these things. It's all in the paper. What I want to do now is up the ante and start talking about autocorrelation, or what some people call lagged correlation. And that allows me to move to the frequency domain. Now, I'm conscious of the time here. So what I might do is go on for a couple of minutes, take some questions, and then anyone that needs to exit, feel free to exit. Even if there's nobody left, I'll continue. We're now all experienced at teaching off Zoom, to the back wall of our office. So I have no problems with doing that. On the other hand, if there's anyone who wants to stay up the back and have a quiet snooze, that's fine as well. Okay, so I want to start talking about autocorrelation, or lagged correlation. So what am I talking about? Just have a look at this plot of a signal. I'll explain what it is later. Imagine I put a piece of plastic on top and I trace the signal on the plastic. I now lift the plastic up and I move it over one time unit and lay it back down. I've now got two signals. Of course, the second one is just the first one delayed by a second. When I calculate the correlation between those two signals, it's going to be very close to 1, but not exactly 1 because of the time shift. I lift up the plastic again, I move it over 2 time units, lay it down, calculate the correlation at lag 2, and I keep going. This is the autocorrelation function, or the lagged correlation function, and it measures the similarity of the signal with itself as you increase the lag. And down here, this is actually the theoretical autocorrelation function. Let's not worry about it, the difference between that and calculating it from the data. I mean, of course, it's important, but just for my illustration of what's going on, you can see in this case that as you shift that plastic along, the correlation is reducing and finally dies out at a lag of about 30. So after about 30 time units in this case, the time series is no longer related to what it was before. So we could say that this little signal's got a characteristic length or a characteristic memory of about 30 time units. That memory is crucial because it's an indicator of dynamics. So when things interact with derivatives physically, that generates memory, and turning that around, when you see memory, then you know there's some dynamics underneath somewhere. So this is crucial, and it's because fMRI signals are autocorrelated, then they've got information about the true dynamical interaction between the nodes, so the interactions over time. But I'm afraid to say this is almost being universally ignored. And by the way, the same thing more or less with MEG and EEG. There have been some work recently beginning to acknowledge that, but I think we've still got a long way to go. So, and then finally, this interaction actually will give evidence of feedback loops in any kind of network that you're trying to study. And so that kind of dynamics, feedback interaction, that's getting to what you would mean by network function. Because if you want to understand how the network is functioning, you need to know what it's doing over time. And this kind of analysis is what you'll need to have to understand that. Now, I want to illustrate with an order regression. I think many of you will have heard of the order regression. You may not necessarily know much about it. It's just a sequential way of generating the signal. So x at time t is a parameter times x at t minus 1, so 1 time lag back. And in this case, I've got a contribution from 2 time lags back. So think of forecasting the temperature. If I asked you to forecast the temperature in Boston tomorrow, think about it for a bit, you're going to say, same as today. Think about it a bit more, you might say, you know, 2 days back is probably relevant as well. Now I'll have 2 parameters. I got a problem with choosing how to weight them. Think some more. You're thinking, hang on, it's May, a year back. There's got to be some information there too. So I need to include that. How are you going to do it? Well, at this stage, you need to talk to a statistician, in particular, somebody who does time series analysis. But my point is, it's a simple idea. It's got memory in there. And in fact, it's got some dynamics. And then there's a driving white noise. Now, one important thing to understand, so let's drop this guy off and just look at this guy. And in fact, let's drop the noise off. So xt is phi1, xt minus 1. Suppose phi1 is 2. I'll start at 0. So x1 is 2x0. x2 is 2x1, which is 4x0. It's going to blow up. So you need a constraint on the parameter to stop it blowing up, as what engineers call stability criterion. Statisticians call it stationarity criterion. So in the case of one parameter, it's easy, the absolute value less than 1. What about when you got 2? Well, you have to construct a polynomial. Z squared minus phi1, z minus phi2, z squared. The roots of that polynomial have to have absolute value less than 1. And you can go on. So the stability is crucial. I'm sorry, but I cannot resist a side poke at the machine learning community, because these guys, yes, I've bored some of my colleagues to death with this already. They, by and large, don't learn any physics. They don't know what dynamics are. They don't know anything about filter stability. And some of the stuff they're doing is consequently quite frightening. And I could go on about that, but I won't right now. Okay, now I want to show you a couple of simulations. These are 2-order regressions, one where the roots of that polynomial are real and the other one where they're complex. When you have complex roots, you get oscillatory type of behavior, and you can see it in the realization. And over here, you can see there's not really anything you'd want to be calling oscillation. Now, the characteristics of the signal are reflected in the autocorrelation function. See, this guy's basically damped oscillation. So it's a brilliant pattern extractor. In this case, you can see some pattern in the signal, but you'd struggle to say what a particular period might be if there was one. So the autocorrelation function kind of extracts some of that, and you could actually try to read off a period by looking at where the thing peaks. Now, there's another quantity even more useful called the spectrum. It's mathematically the Fourier series corresponding to the autocorrelation, but don't worry about that if you're not happy with the maths. Have a look at this spectrum here. It's very peaky. What it's trying to tell you is that most of the variance or the energy in this signal is concentrated in a narrow frequency band. So there's a theorem which allows you to decompose the total variation of the signal, kind of like an analysis of variance in the frequency domain, into contributions from each frequency band. And the point is, when you've got a signal which is heavily oscillatory, most of that contribution is going to be in a small frequency band. And the spectrum is telling you that. So very powerful object. Over here, this spectrum has got most of its energy at very low frequency. Now, what is that telling you? It's telling you the signal is fairly smooth. It doesn't change rapidly. And when you look at it visually, indeed, it's wandering around, but fairly slowly. I could give you other examples. You can construct examples where the energy is all at the high frequency, but I think that's sufficient. So that's my attempt to give you an intuitive idea of what this stuff is. Now, why does this matter? Now, listen, I'm going to take that break because it's almost time. So has anyone got any questions about anything at this stage? Yeah.
You mentioned difficulties in constructing a threshold to
yes.
reduce the number of connections. Would a model that is sparse, wherein the actual then covariant structure amongst the variables itself is sparse, would that in essence provide, one could construct one, the zeroing out of the different
yeah, so when you would add the sparsity penalty into your model fitting, then as I said, you'll get the automatic zeroing. You could expect to get more zeroing because you'll be statistically efficient. But when you're not statistically efficient doing what we were doing, you're going to end up on average keeping some links that you should have thrown away. You might occasionally, throw something away that you could have kept, but it's more likely that you'll keep things you should have thrown away. You still have the problem of choosing that lambda, but you won't need to do these massive simulations to do it because, there's standard model selection methods, which you in particular know about. So yeah. And in fact, I'll be showing you how we do this in the frequency domain example in a minute. Okay, so I see nobody's leaving yet. Maybe, I don't know, feeling tired. So let's continue. Okay, so I want to now...
I have one question.
Oh, somebody got a question there?
Yes, I just wanted to know, for the null distribution, do you estimate the white noise, you get it from the data, or is that you just have a simulated white noise, which
yeah, right. Okay, so the question is talking about getting those null distributions. So you're going to simulate the white noise, but we're going to use exactly the same processing stream. So because we simulate it, because we know variances, for instance, but we actually don't use that information. We estimate anything we need from the white noise data because we need to apply the same processing stream that we're using on the real data. So yeah. Okay, so let's talk about taking this to frequency domain. Why do we want to do this? Because we want to extend the network construction to deal with autocorrelated signals. So the construction I showed you already makes no mention of autocorrelation. Those correlations that we were starting with, they're all zero lag, instantaneous correlations. We want to use the lagged correlations. Now, people started trying to do this roughly 20 or so years ago and went off in the wrong direction. And so the idea was, well, if I've got a lagged X, I'll call that another node, and then I'll look at links between that. The problem is, in a big network, these lagged things could go on for some number of lags, and the whole thing explodes exponentially. Complete disaster. It's not the way to do it. The way to do it is through the frequency domain. Okay, so, and also, we're going to join that together with vector order regressions, state space models. So there's a small literature here. There's a handful of statisticians and the odd engineer running around trying to do the same thing as I'm doing, but they're doing it on scalar networks. But they haven't realized the way to go is with vector order regressions. They're trying to do it non-parametrically. So non-parametrics, I could go on until midnight about this. I'll just make a couple of quick comments. The claimed advantages of using non-parametric methods is that it's model-free, that you're not making particular kinds of assumptions. I dispute that. For the mathematicians, you show me one of these things, I'll find a Fourier series hiding somewhere, together with some of its coefficients that are actually being used to construct this non-parametric thing. So that's another story. I need to write a paper about that. But the other problem is that from a mathematical point of view, the approximation properties of these non-parametric methods are miserable. If instead you use things like autoregressions, you get phenomenal approximation properties. This is actually some classic maths. I'm not going to attempt to go into it. In order to have those terrific approximation properties, you need to assume that your underlying objects are extremely smooth. But in most of these applications, they most definitely are. So it's just crazy not to try to use that information. And basically the way you do it is by using these state space and autoregressive type models. Okay. So here is a vector autoregression of order 1. So instead of the scalar parameter, it's now a matrix in there. And the noise is a vector noise, so it's got a covariance matrix. Now, I didn't talk about the formulae for those spectra that I showed you, but there are formulae. I'm not going to try and explain how we get them, but here it is. The shift here explains the e to the minus j omega. By the way, j is the square root of -1, just in case I need to explain that mathematicians use I for the square root of -1. If you see somebody using j, you can be sure is either a physicist or an electrical engineer, neither of which would ever consider using I. The other problem is the definition. So where I have a minus j, a mathematician would have a plus I. One of those intriguing things. Anyway, so there's the formula. It's got the inverse of this thing. Now, what's going to happen in the frequency domain is that the correlation matrix will be replaced by the spectral matrix. Okay, so then we will need the inverse of the spectral matrix to develop the frequency domain diversion of the conditional independence graph. So here is I'm just inverting this relation. It's just matrix inversion. Here it is. Now, here is the really interesting thing about this formula. Now, I'm not claiming to be the first one to have discovered this property. I maybe claim to be the first one to have used it to do anything. The thing is that the only thing that needs to be inverted on the right-hand side is the noise covariance matrix, and we've just spent a whole stack of time discussing how to do that. But the dynamics captured in the A matrix, there's no inversion. So you can read off, so you need to read out the frequency domain version of the partial correlation. So what is that? It's called the partial coherence. And from this beautiful little formula, I can pretty much just read them out. The only thing I need to invert is the sigma, but the dynamics will just come with it. And that just saves you, I mean, so many orders of magnitude of computation. It's just incredible. Now, what about the formula for the conditional? Now, I now call it trajectory mutual information. This is my own terminology because I want to continually remind you that we're talking about a time series. Again, you read those papers that you find on the web, nobody's talking about mutual information between time series. If they are, they're treating them as white noise. So it's always only instantaneous mutual information they're talking about. And I'm not doing that. So I've got this special phrase, trajectory. So there is a classic formula. I didn't invent this. It was discovered by famous Russian probabilist, in the 50s. Yaglom, I think, is the name. So it's the frequency domain version of the formula I showed you before. This is Gaussian land again. -1/2. Now the integral over all frequencies log 1 minus absolute squared conditional coherence of time series A between time series A and time series B, having regressed out all the other time series. Okay. And now we would like to do a sparse modeling. So the way that we're doing it currently is 2 stages. So we first fit a sparse vector order regression to the network. So think of that 167 parcellation. I'm keeping a couple of hundred time series in each parcel. So I've got a gigantic dimensional time series. I've got a bit of a problem still because I've only got 1,200 time points, but we'll worry about that later. I'm going to fit a gigantic vector autoregressive model to that. That's going to cause me a problem because the A matrix is huge, and I may want to apply sparsity right there on that A matrix to cut down the number of links. And that's essentially what we're going to do. The example I'm going to show you only does a scalar network, not a vector one. And I'm starting to work again with Patrick Purdon's lab. They've been developing some state space stuff, and I guess we're hoping we can bolt some of these things together. So at two stages I'm doing at the moment. I first just fit the sparse order regression. And then once I've got it, I compute the mutual informations between all the links that are left using this formula, using this formula down here. So it's computationally cheap. And then I do an additional pruning with another set of null distributions to do some further pruning. And then finally, I've got my finished dynamic network with my thinned out links. I've got link strengths for each of them, and I'll talk about the meaning of those conditional mutual information link strengths in a moment. So this is a paper published in IEEE Transactional Medical Imaging 2015 with former PhD student Ben Cassidy and my colleague in the University of New South Wales Medical School, Carolyn Ray, Lindy Ray. She runs the UNSW research fMRI scanner. So we basically did what I just told you. I don't use L1 penalties, I use L0. I'm not going to go into technical details, but basically the L1 introduces some bias that I didn't discuss. The L0 doesn't, but it's a bit more challenging to work with. And then I just do what I said. So here's some results. Again, I'm not going to go into interpretation. So these are our results. Again, the greener, the stronger the link. So this has now got dynamics in it. This is off a scalar network. This thing looks a lot richer than the sparse one that I showed you earlier, which was not using lagged correlation, okay? So it's very clear that using that lag correlation is getting you more. Down here, I've got the same thing, actually with that same algorithm that ignores the correlation. And it's got a very, very dense network. And then this is clearly a problem because it's getting confused by the strong autocorrelation. Now, this one, I really would rather not talk about this because it's a bit embarrassing to a very distinguished researcher in a lab in the United Kingdom. I'll have to utter his name in a minute. What happened was when we submitted the paper, we didn't do this comparison because they had done something a little like this before us. But they didn't know about the autoregressive stuff. So they're trying to estimate all these partial coherences. So I think we've got 90 parcels. So it's about 4,500 partial coherences. There's no time series analyst on the planet who knows how you would estimate that. Because usually you do it non-parametrically. When you do it non-parametrically, there's a window width that you have to choose. At 4,500 of them, nobody knows how to do it. So what do? They set them all equal to the same value. And so when we did the comparison, we were forced to do the comparison by a reviewer who basically said, well, hang on, Bullmore's group did some stuff like this, so you need to compare. So we had to get the software off Bullmore's postdocs, and the comparison shows that their method is basically, missing most of what's going on. And it's because of this extremely crude estimate of the partial coherences. So I think this is actually a demonstration of what I was indicating before, that if you're going to try to do this non-parametrically, you're going to miss out on a ton of stuff. And using the autoregressive and state space approach is really going to capture all that kind of information. Okay, so, and then we're still doing, at that last step, we're still doing the massive simulation. I mean, the theory here is even worse if it could ever be worked out. Okay, so I wanted to, now listen, it's 2:45. I will definitely shut up at about 5 or 7 minutes. I'm nearly there anyway. Granger causality, I mean, a number of people have been asking me about this, and I made some comments in a meeting the other day. In the interest of time, I'm not going to go through this slide in great detail, but I want to draw, I think some of you will know in the Granger causality, you get measures of the strength with which one time series pushes another as a log of a ratio of prediction error variances from doing some regressions. You get a measure of the pushing in the opposite direction. There's a decomposition of a total trajectory measure of the relation between the two time series, which can be decomposed into a sum of these two directional measures plus an instantaneous measure. So this is due to an econometrician, John Gewicki, a famous guy. Okay, I better back up and tell you what I got here quickly. Suppose you've got a catchment area where it rains, the water then either off the surface or in the water table goes into a river. So you're going to measure the river level and you're going to measure the rainfall, and let's assume it's in the tropics, so it's raining all the time. Now suppose you want to predict the river level. Well, the simple way using an order regression is a regression based on the history of the level of the river, and you'll get some prediction error variance. What about also using the history of the rainfall to predict the river level? Because we know the rainfall causes the fluctuations. So if you included that history in your regression, you'd expect to do better. So you would expect that your prediction error variance based on the history of the river level and the history, the rainfall and the river level would be smaller than the prediction error variance based just on the history of the river, the level of the river, in which case this ratio is less than 1. And so you'll get a log of a negative quantity. If they're equal, then you'll get a 1 and a log of 1 is 0. Similarly, we could do the thing the other way around, except when we do it the other way around, using the past of the river level to predict the rainfall isn't going to do anything for you because the causality runs in the opposite direction. Okay. Now, suppose I give you two time series, but I do not tell you which is the river level and which is the rainfall. Of course, if you're a hydrographer, you'd look at them and know the difference, but let's not worry about that. You then do the 4 regressions. You then calculate these quantities and you discover that one of these measures is 0. Then you're going to claim that it's one of the other time series is pushing this one and there's no pushback. And you're going to be able to claim that you can recognize which was the river level and which was the rainfall. So that's the idea. There's been criticism of that since Granger came up with this in the 1970s. It's, shall we say, not quite as simple as I described. But what I wanted to say was that there is two things. Gewicki wrote some terrific papers in the early 80s in which he showed this decomposition. And then shortly after, an engineer, Jorma Rissanen, a Finn communications guy, realized that actually it was a decomposition of mutual information into directed mutual information. So the overall mutual information, trajectory mutual information, is a sum of 2 directional measures of trajectory mutual information plus an instantaneous measure. So this is brilliant because it means that you could try to generalize this thing beyond linear time series models. So there's been some work on that and I've contributed to that. Here's the problem. You can't use this on fMRI time series because everything's being filtered by a hemodynamic response function. There are delays, that's not a problem. There's inhomogeneity across the cortex, it's not a problem. The problem is that the hemodynamic response function is not a stable filter. So in essence, to get the Granger causality, you've got to undo it. So you have to do an inverse filtering and you can't, because the inverse filter blows up. And so what that means is, in practice, you can mess up the Granger causal relation. So I wrote a paper, it's cited here, spelling out the theory and giving examples of how I could simulate a system where, say, A was causing B, filter it with a hemodynamic response function, do an analysis, conclude that the causal effect was the other way around. Okay, so basically hopeless. That is, if you're going to use Gaussian methods. You might be able to do something by using non-Gaussian methods, but intuitively, the closer you are to Gaussian, the more difficult that will be. Nobody's actually really worked out how this might be done. There's related literature in signal processing, but it's really still an open question. With MEG, totally different story, because there's no hemodynamic response function, but you've got to solve an inverse problem in order to get your source signals. Those source signal estimates will be noisy, and the econometricians have known for decades that when you inject noise into this story, you can also completely mess up the Granger causal relationships. That may not be the end of the story. I'm, trying to look at this, and I would say it's an open question as to whether or not something could be done. We'll have to see. Okay, so look, final comment. We really need to have a discussion about how do you do spatiotemporal network construction in neuroimaging. So I'm advancing the argument that the answer to that question is to use conditional independence graphs and, sketching out the extension to time series. But what are we doing currently? Well, we already talked about correlation, still dominates. Then there's PCA, ICA. You basically get a collection of eigen time series and eigen spatial maps, if you will. And then, of course, you then threshold these eigen maps, and that gives you some networks. The problem is, with each of those networks, there comes just one signal. That's kind of weird. If I show you a network, which I claim has got something to do with the functioning of the brain, you'd expect to see different signals at each of the nodes of that network, but this method is not capable of producing such a thing. So there's clearly some conceptual problem here. And of course, it's also related to correlation, because it's ICA not exactly, but PCA clearly. So there's also some issues there. It's not been sorted out. We need to get on and look at this more carefully. Now, here are some other questions, huge questions. How do you compare networks? So, if I construct a network and claim it came from a healthy subject, and you construct one and you claim you think this has come from somebody who's got some early stage of dementia, on what basis are we going to claim those networks are different? At the moment, it seems we're just eyeballing things or doing some other kind of very crude stuff. It's just not sufficient. So we need formal methods. And again, in this grant we're writing, I'm trying to work out some of these things. And then even worse, because actually what you would rather like to be able to do is, given a collection of networks, to classify them into different groups based on the network structure. We don't really know how to do this, and there is almost no literature anywhere trying to do it. In the STAT community, they've gone off on a side tangent, looking at multiple networks, but doing a global sparsity penalty, which actually draws the networks towards each other. This is bad news, because if you want to be able to determine if one network is anomalous, you don't want to bias it by drawing it to all the others before you start looking at it. So it's just not a relevant way to do things, but that's what they're all excited about. Then, of course, there's the multi-subject story. We're still in the situation where that's all being done in an ad hoc way. Even worse, there are some techniques running around which are actually wrong. And what we really need is what I call a network analysis of variance, which would enable us to decompose the variation in a group of networks into variation within the individuals across the multiple scans, and then between the individuals. And again, I've got some ideas about how to do this, but it's not there yet. And finally, I just mentioned topology. I've already done a bit of work on this. basic thing about topology is you're trying to get at the shape of things rather than detailed quantitative specification. And this is an issue because if we get some results using a parcellation with 90 parcels and you do an analysis with 167, we'd like to know that I'm getting a coarser version of what you got. The evidence would suggest it doesn't really work quite that nicely. So we need to have methods that are resolution independent, and these topological things which are just coming along offer the possibility that we might be able to do that. So we've done a bit of that, and we're using some frequency domain methods in there as well. Okay, so that's basically it. Again, if you don't get anything else out of this, just go and have a look at Whittaker's first few pages and start repeating what he said. And then I think you'll start to get worried. So I'm basically saying the correlation methods are hugely problematic, that conditional independence graphs or conditional independent networks do provide a principal framework for building functional brain networks, but when coupled with conditional mutual information, because that's how you're going to handle the vector signals at each node. And then you can do it all. You can handle true dynamics in time and so on. And but still there's a stack of open questions. Okay, so my collaborators. Now this slide is a couple of years old, but I don't think anybody here is going to complain because you look younger in this slide. And I just, so this is Lindy Ray from my university. Ben Cassidy, the former PhD student, now working in a venture capital firm. Martin Lucy, Swiss postdoc, was in Muddy's lab and did the early work on our paper. And Du Bois-Bowman, who at the time, so he's a statistician, PhD statistician. He was head of biostat at Columbia, so that's where Ben did his postdoc. Du Bois is now Dean of Public Health at the University of Michigan, Ann Arbor. And then I've got a couple of extra references if anybody's interested. Okay, so that's basically it. So any questions? Maybe not. Yeah, Abbas, yeah.
Formulated this, but I was wondering, I mean, this is in line with what people do with multivariate analyses to basically either estimate Granger causality, or basically removing interdependency between, let's say, different time courses that you're doing, say, so that basically prune out possible interconnections.
Mm-hmm.
How would that, I know it's a different approach, but how would that be related to this?
Yeah, where does that occur in what I'm doing? Yeah, good question. So that first stage where we're fitting the sparse vector order regression to the whole network, that's when you're getting rid of lagged links as well as other kinds of links. So that is then getting rid of those things that might be, are not in fact causing a problem in looking at the dynamic relationship. And the ones that are left will then be the ones you need to regress out to get your partial coherence.
Basically, isn't that what the partial coherence is kind of doing?
Partial coherence ignores lagged correlation completely.
So, but that also.
Yep. Okay.
So, because one problem with that is if we miss a node or in comments, then everything gets messed up.
Yes, great question. There's a whole swag of issues with that, some very nice mathematical embarrassments, which I haven't got time to go into. And I'll say up front, we don't have quantitative methods for managing that. So suppose, for example, somehow you do this analysis and you left out a node, I don't know, let's say it's in auditory cortex, somehow it got left out for whatever reason, something glitched, who knows. You're doing all this analysis, but there's some signals there which would affect your result, but you were not correcting for them. So you could cause some bias. I think until we start doing this, that is, let's go back, look at the data we got, leave a few judiciously chosen, possibly even parcels out, do this whole analysis and see what you get. So that would be one empirical way of chasing that question, hasn't been done. In the meantime, of course, one would like to develop a theory. I would call this a kind of sensitivity analysis. If I tweak some parameter, what's the effect on my result? So yeah, these are great questions and they need to be looked at. What I would say on the positive side, we're producing functional maps that look like DTI. So we're clearly getting some valuable information. So it's not like one node could, make sufficient difference to cause a huge problem. Cerebellum is an issue. We found there's some kind of dominating components there. So there's a number of issues related to that that are worth pursuing, yes. Yep. Yes. Yes, a great question, and you're right. I should have said something about these corrections at the beginning. I've kind of been assuming there's been some pre-processing, but there's a problem with this. I pointed this out a long time ago, but I don't think anybody's taken any notice. Because we're doing two things. We're doing a pre-processing and then we're doing some more processing later, claiming that we've got clean data. Actually, when you look at what you're doing from an optimization math point of view, you should iterate that. So having done the processing, you go back and, redo the pre-processing and keep iterating until it settles down. So that's one kind of thing. I mean, I'd need to work out how you were going to do it. The second thing is there's some kind of an issue with the correlations, because once you regress out physiological effects, for example, you've got what you're left with is some kind of a partial correlation because you took out the effect of some signals. But then you carry on as if that didn't happen. And now you get, what I've been calling the partial correlations. There may be some bias issues in there. So no, I haven't looked at it, but it's a great question. And yes, it absolutely needs to be looked into. Again, I would say that we're getting results that make sense. So I would not be expecting that a proper analysis of these issues would show us that what we're doing is totally useless. But it may show us that there might be some regimes in which, shall we say, we need to be extra careful or possibly do things a bit differently.
Maybe you kind of explain this, but specifically, if you're looking at fMRI data, which is extremely slow, or one other way to say it is that in your model order will be very high if you want to capture the delays, right? Because you have to look at many delays, or at least your delayed steps have to be large enough, right? Because it's if you want to predict the future values using the past values, you have to go far. It's a very slowly changing signal, probably, right? So
yeah, you don't need to go far, but I'll answer that in a moment. Yeah, continue.
No, but that was my question. If you have
Oh, I see. Okay. So here's the answer to that question. If you just did an order regression, then you may have a problem not being able to get away with a first order regression requiring extra lags. If you use a state space model, and they're closely related, then that's basically an ARMA model. And then you got a more compact representation of the lagging. And in fact, you can always do it with a first order state space model. The difficulties then arise in the observation part of the story. So short answer is no, that's not a problem. We'll probably need to have some further discussion, so I'll spell it out for you. I mean, it's a good question, but no, I don't think that's an issue.
Hello, can you hear me?
Yeah, go on.
Hello, thank you for the presentation. So my question is I would like to know if you have any experimentation with data where you not only can assess the null hypothesis, but you actually know the ground truth, the connectivity, the true connectivity between systems. Let's say that you build a I don't know, like a Lorentz attractor. You assess some that you let it oscillate with Runge-Kutta fourth order, let it achieve some level of stability, and then you try to measure this, and then you increase the noise.
Yeah, right. Yes. Okay. So the question is a ground truth question. So have we got any examples where somehow we know the ground truth and then we apply our methodology and show that we're getting a good approximation? And the short answer is no. And of course, that will be a phenomenal exercise for which one would need to have a large lab. But I think maybe Patrick Purdon's lab with their anesthesia focus may be able to tackle some bits of this. And then if we talk about MEG and TMS, we might be able to tackle some things there. So I don't know, knock out everything except one and see what you can say. But yeah, we're talking about a big project here. I mean, multiple laboratories over periods of time. But absolutely, that kind of thing would be great to do. I think outside my skill set.
Okay, so if I may, just to in a way, thank you for your effort. Let me just share that I've done many experimentation, just try to empirically assess the virtues and maybe the problems of different metrics, different connectivity indices in this way. And empirically, what I've observed is that what comes as counterintuitively, just normal correlation normally is a not that bad index. It is worse than others, but it's really not that bad. So it's kind of like a good trade-off between simplicity and a reasonably not too bad index. Although there's much better, like you were mentioning, mutual information. But mutual information, my experience with it is that it requires too much data, and it suffers a lot when the noise levels go high.
Okay, so let me answer that. So he's saying he's done some experimentation. He's compared lots of metrics. He finds correlation works pretty well, and mutual information is problematic. I'm not doing the mutual information non-parametrically, which is what everybody else does, and that's why they have these troubles with it. So I'm using parametric models, and that's why I'm getting these very good results. That's the first thing. The second thing is, once I've built the partial correlation network, then I can invert that network partial correlation matrix and get back a correlation matrix. And so wherever I find a reliable partial correlation matrix, there'll be a reliable correlation matrix that goes with it. They'll all be consistent, but the problem is you can't interpret them. So that's the issue. But listen, why don't you send me a few of your papers and we can have a look at that.
Absolutely. Thank you.
Okay, great. Yeah. Sorry, I couldn't work out how to up the volume. All right. So anybody else? Oh, sorry. Yeah, I wasn't even looking at that. Let me. I'll have to stop the share. Where do we go? Here we go. All right, maybe I missed some part of the beginning. Hang on a sec. My question may be a generic question. When you apply L0, is there any way to avoid local minimum problem? Yes, okay, so I didn't mention that the L1, so this is a kind of mathematical issue. When you have the L1 penalty, you get what mathematician calls a convex problem. It's got a unique minimum. This is the reason that this is popular. However, you know, if you look at what people were doing, I mean, pretty much anywhere else, any discipline you like to name, have been solving non-convex optimization problems for decades. So the idea that you couldn't do that because it's not convex, I think, is complete nonsense. But yes, of course, you have the problem that you should be worried about local minima. But when you get L0 networks that firstly make sense based on domain knowledge and are a lot sparser than the L1 networks, which we now know very well mathematically are biased, then I think you've got increasing confidence that you can make these things produce something useful. But there's certainly more theory to be done to sort that story out. Yes. Yes. Absolutely. Great question. Yeah, I mean, I didn't emphasize these more mathematical computational things, but for sure. Okay. So what we found, and I've been doing L0 for 20 years. So, and basically because everybody said you couldn't do it. So I thought, what the hell? Let's just do it. So what we found was we usually initiate with the L1 solution. We try other solutions. The classic stuff is, you know, random initialization, all that kind of jazz. We did all that. We basically found you initialize with the L1 solution that seems reliably to produce good results, repeatable. So, you know, it's a general statement, but I think that's a good place to start, at least. Yeah. Yes. Yes. So I would say again, as an average statement, that's what we were getting. Okay, anything else? All right, I think it might be good to call it quits at this stage. Thanks very much for everybody that came and those that stayed. I didn't hear anyone snoring, but I don't know, I haven't been tested in the audio lab recently, so who knows. Okay, great. Thanks a lot. And the talk will, you know, be posted, so you can get hold of it if necessary.
If you ended.
Yeah, just end it. Yeah.